All right, let's work on part E. So you have 1 over a quadratic. Um, you can check if you can factor the quadratic into simpler linear factors. Um, but it's going to be hopeless because the discriminant, if you remember the quadratic formula uh, for this quadratic here, so you have the discriminant, which is written as b squared minus 4ac. Okay, so here a equals 1, b equals -4, and c equals 9. And b squared is 16 minus 36 is what the discriminant is, and you don't have any real roots. That's minus 20, less than 0. You don't have real roots, which essentially means that you can't really factor the quadratic in terms of having real number roots. So your last resort here to simplify the bottom is maybe using uh, maybe completing the square. That could be one way to go since we can't factor it, right? We can't use, I think, adding and subtracting would not help because there's only a constant at the top. I think we have the only option here is the completing the square. So let's try that out. X squared minus 4x plus 9. So the way I do it quickly is the following. So since I have -4 here, so I'm going to take the half of that. Okay, so it's x minus 2. I'm going to write it together with this x here. So I'm going to write this as like quantity squared. Okay, so x plus the half of the coefficient of x essentially. That's -2, so x plus -2 is just x minus 2, quantity squared. So if I ever expanded this out, what would I get? It's a quantity squared, so x squared minus 4x plus 4. Okay? Okay, so x squared minus 4x is fine. But I have this extra 4 coming in by completing the very first two terms to completing the square. So I should probably subtract that 4 from here. Okay, so that's the payback. I still have plus 9. Okay, I still have plus 9. So let's simplify that. So this is x minus 2 squared plus 5. And there are formulas if you prefer to convert this quadratic in this perfect form. Feel free to use them. I'm just showing you another way to handle the same completing the square. All right, now we should figure out what the resulting integral is. So dx over x minus 2 squared plus 5. Well, at this moment, we can go back and check if there is any applicable basic integration rule that we can use. Out of all of them, if you stare number 19, I think that is the closest. But I still need to modify the given, the final integral by using a u substitution. So you have du over a squared plus u squared. That's a very similar form. The form we have is very similar to that. And then this is integrated as 1 over a arctan u over a plus c because we have the sum of the squares, right? So I have dx over x minus 2 squared plus, I can rewrite 5 as radical 5 squared. Okay, so this way I can call u to be x minus 2, and a is going to be radical 5. But here I can immediately write du equals dx, so that this integral turns out to be du over u squared plus radical 5 squared, right? All right, this is integrated as 1 over a, so now I can take a to be radical 5 in the formula. Let's go back to the formula, and then just reread that. So we have du over a squared plus u squared. That's 1 over a arctan u over a plus c. Here we go. I'm going to write that as 1 over radical 5 arctan u over radical 5, but u is x minus 2. Let me just write everything in one shot. Okay. So u over a radical 5 plus c. Okay, I think that takes care of part E, where we use the completing the square. Again, the technique that I used here is just for me a shortcut. If you know any other technique, go ahead and apply that technique. There is a formula for completing the square. You're welcome to use that. But the whole idea is here to see that you have to complete the bottom of the integral to a square. If you can see that, the rest is just a little algebra. All right. So let's move on to part F. Okay. So I have x times 3 plus 2 over x squared. Okay, so you can consider all different things, like applying the u substitution maybe for the inner side of parentheses, but that's probably does not help. Let's go back to, and this is not looking like one of those known integrals. So let's go back to the procedures for fitting integrands to basic integration rules. I think in this case, expanding the quantity square would be like a good way to start with. Like it says, expand the numerator in general, but expanding is one of the techniques, right? So expanding like quantity square term could be like one of the things that we can consider. In fact, there's x outside, so x times that expanded expression is gonna take us to a nicer expression for which we can use the power rule for integration. Okay, so let's try that out. I am going to rewrite this as 2 over x quantity squared. So here we go. I have 3 squared to be 9, twice of the first and the second. So that should be 12 over x, I think. Okay, good. And then I have 2 over x quantity squared. That's 4 over x squared. So now I'm going to expand this whole thing all the way. So x times 9, x times 12 over x, and then x times 4 over x squared, so that's 4 over x. Okay? And I can also rewrite this in the simplistic form, so I'm going to put this 4 over x as like 4 x raised to the power of -1. Okay, so this way I can handle each term separately. So I can go ahead here and I can do everything in one shot, in fact. Okay, so 9x plus 12 plus 4x to the power of -1. Okay, dx. Okay, there we go. So now I am integrating. So let me just write with yellow. So, well, the first one is 9x squared over 2 by using the power rule. And the second one is 12x. And the last one is a very special integral, by the way. 4x to the -1 or 4 divided by x. Let's go back here. Well, first of all, 1 over x dx is integrated as ln x plus c in number 5. Okay, number 5. Right? If u equals x in number 5, dx over x is ln x plus c. So that's where the power rule for integration not working for the case where you have n equals -1. Right? Number 4 doesn't work because if n is -1, it's 1 over u, and 1 over u has a separate formula that is ln absolute value of u plus c. So we can go back and write this as ln absolute value of x plus c. I just wanted to do this like a little bit longer for you to see that the last term 4 over x is integrated as ln x, but I should also add the 4 here. Okay, so it's 4 ln x, ln absolute value of x plus c. All right. I think this was a good example, at least to try out a few techniques here. You can also practice other techniques by yourself, like dividing an improper rational function. We did adding and subtracting terms in the numerator. We did not have any example for us to use the trig identities, and we didn't use the conjugate business here. But there is going to be more integrals along the way, so that we're going to go back to this basic chart to follow the techniques here. All right, I think that takes care of all 6 parts of the exercise. I think we are completely done. Then I'll see you in another video. Bye.